Okay, so very happy to have Roman back for part 2 of his talk on generalized quantifiers in arithmetic. So go ahead, Roman.
All right, thank you, Atar, and thank you all for coming again, and welcome all of those of you, just one, who were not here last time. I will make a brief introduction to the whole lecture, and then I will proceed with part 2. Parts are independent, so it doesn't really matter much if you were here last time or not. I just will quickly retell the story here. And the important thing is not really talk about mathematics with all the details and proofs. It's a sort of history talk about an episode in history of model theory of arithmetic that started in 1980 with a paper of Angus McIntyre, and you see Angus here on the left of the screen. Oh, let me see. Let me do the full screen. Oh, I don't know. Oh, now do you see a green frame?
I do. I'm not sure what.
Okay. Let me try again. So maybe I will. Let's see. Let me try again. It's not very bad, but it shouldn't be there. Let me try again.
Frame in the end.
Okay, how is it now?
Looks good.
Okay. Okay, very good. So so this whole story was this episode in some developments in model theory of PA, and it started with a very influential and interesting and well-written paper by Angus McIntyre from 1980. It was about the role of Ramsey quantifiers in arithmetic, where he proposed certain problems and proved certain results, and in an interesting way. And this was all in response to the Paris-Harrington and Kirby and Paris results, combinatorial independence from PA. And the goal was to sort of, instead of extending the axioms of Peano arithmetic by adding new true, but unprovable combinatorial statements, to extend a logic a little bit in a somewhat modest and somewhat conservative way, but that would allow to actually prove all the combinatorial properties in natural ways. And he suggested to use Ramsey quantifiers that were previously introduced and studied by, again, an influential paper by Magidor and Malitz. So this was the content of part 1, and I will sort of make a brief summary of the results, and I will move to parts 2 and part 3. And you can see Jim, Angus proposed certain, left certain things unproved, and one in particular, he proved for his version of Peano arithmetic with Ramsey quantifiers, he proved completeness and compactness results, but that used Magidor and Malitz technique with some extra set theoretic assumptions, diamond. And then Jim and Steve Simpson, who's to the right of Jim here, took up the challenge and actually wrote a very nice and clear paper. When they solved McIntyre's questions, they proved completeness and compactness in ZSC, and using Geifmann's techniques of minimal types, and proved other interesting results. And then the last picture on the right, two small figures. There's Jim again, also in Oberwolfach. Steve Simpson is standing in Oberwolfach, and here is Jim and I standing in Oberwolfach. That's where we were writing the book that you know. And I had some small contributions to this whole project to sort of to see how one could use generalized quantifiers to study models of PA. And I will mention this today in the second part. So let me quickly move forward. Oh, and by the way, last time there were certain typos on the slides. Now they are corrected. I realized that one of the features of having all these talks recorded is that when they are recorded for posterity together with the typos, it's hard to correct typos on the video recording. But so if you see anything that's wrong, let me know so we can correct things live. Okay, and okay, so let me quickly move forward. So this is the quick outline of the previous talk. And so this is what I ended with last week. So this is the upshot. This is the concluding results of this paper by Simpson and Schmerl. So just I reminded everyone, what are classes in models of PA, and this is the completeness theorem for Peano arithmetic with the Ramsey quantifier is you add a quantifier that says that there are many quantifiers that says that for a definable set in a two-dimensional definable set, there is a homogeneous set. There's an infinite homogeneous set, and PA together with the language with all those quantifiers is Peano arithmetic when the induction schema is extended to the language with those additional quantifiers, and the proof is based on a construction of models of PAQ star. And I went over this last time. And the upshot is that they construct models that I called now Schmel-Simpson model, and they have interesting features. They all have to be kappa-like for regular cardinal kappa. They all have to be recursively saturated. They all have to satisfy con-PA and much more. And actually, we'll see in a moment how much they have to satisfy. But they have this additional feature that in the language of PA together with Ramsey quantifiers for pairs. Sorry about that when I touch my mouse. This moves. So the definable set in the languages Ramsey quantifiers are exactly the classes of those models, and that includes many undefinable classes as well. And more specifically, that some details of the proof, they give you this corollary. And a weak model of PAQ star. A PAQ star, the sort of when you say there is a homogeneous set, when you interpret your Ramsey quantifiers, then you just mean a set, and that's an unbounded subset of the universe of the model. But you can restrict this existence quantifier to some family of subsets of M, and that makes a weak model of PAQ star. So this fractor X here denotes a family of the subset of a model M, and MX is a weak model of PA. And if it's a weak model of PA, then if you look at now as a structure for second order arithmetic, and if you look at the definable subsets, second arithmetic definable subset, that it is a model of pi-1-1 comprehension. And much already follows from it. It follows that the model has to be recursively saturated. It follows that it has to satisfy con-PA and many other things. And conversely, that every model of pi-1-1 comprehension is a weak model of PAQ square. So this gives you this sort of source of weak models, and then Schmerl and Simpson construct strong models, which means that you interpret the Ramsey quantifiers in the whole power set of the domain.
Roman, can I ask
Sure.
on that slide, is that theorem true for every strong model of PAQ square? Is that what a Schmerl-Simpson model is? That just a strong model?
Oh no! This is a specific. I mean, the first theorem of in the middle of the slide. But
Right,
this is
theorem,
specifically about it's specifically about this construction, not every model.
And so,
so it's all. Yeah. Go ahead.
I would think that the argument would kind of be the same, right? Because to show that a class is definable in this sort of structure, you would kind of say that you have unboundedly many codes and something along those lines, right? And so I would think that might generalize beyond this particular construction.
See, so maybe the one containment that all classes are definable, perhaps maybe because do this definable witness theorem, and maybe you could somehow approximate it, but I'm not quite sure about that. This really applies to this, not because what they do construct you construct those rather classless models in the language that's extended by counting the many new unary predicates. And so this rather classlessness is very specific to the construction. And it's open whether there are some other models. Maybe there are some other models, and there will be something in open problems about that.
Okay.
Can I just quickly?
Yeah. Go ahead.
Sorry,
Go ahead.
The question that Atta is asking, whether every strong model could work in the middle theorem. If we think of the smallest strong model, that would be just the natural numbers with a full power
standard
set.
model, right?
Yeah, and then the theorem falls apart there because
that's right. That's right.
Yeah.
Because there are too many classes.
There are too many. Yeah, makes sense.
Oh, that's right. But right, once you have the two, more classes than the cardinality of the model.
Yeah.
Then right. Thank you, Ali.
Thanks, Ali.
Sure. Okay, and then the other important consequence is that they show that the PA consequences, so the statements in the language of PA that are proved in PAQ squared, are exactly the consequences of pi-1,1 comprehension. So that shows exactly the strength of that theory, and in particular, they refer to the provability of Paris-Harrington principle and some stronger statements from the paper of Friedman, McAloon, and Simpson. And so this was the end of my talk last time. And also I mentioned that all those papers, the McIntyres and Sperl and Simpson, and also a paper of Karl Morgenstern that I mentioned, I only found out about it lately that Laurie has a very nice review of those papers in, I don't remember where there was a reference. Laurie, where is your review?
I don't remember. I thought you told us last week.
That's right.
But I wasn't there. But I wasn't. I watched you on YouTube.
Right. No, it is noted. I don't want to go anyway, but it's a very nice, very informative review of all those three papers. So I just wanted to mention that. So let's move forward. And this will be a very short segment on hyper-Ramsey logic. And this was a paper of Jim. As a sort of a follow-up. And I only, in this definition here, I have this Q11 quantifier, which just says, there are many elements such that phi of xy, if and only if there are unbounded subset x and y, such that for every a from x and from every b from y, phi of ab holds. So it's a sort of very weaker Ramsey property. But Magidor and Malis, this is like the weakest of the quantifiers. Instead of 1,1, you can have 2,2, and it would correspond to two-dimensional Ramsey quantifiers. You have a sequence of exponents, and would have quantifiers corresponding to existence of homogeneous sets for several, the sort of so the quantifier says that if you have a sequence of n different exponents, the quantifier would say there are n different unbounded sets, and those are subset of given dimensions. And then for every selection of tuples from those, something holds. So this gets a priori, you get stronger and stronger expressive power in those quantifiers, and Magidor and Madid study those quantifiers, and Jim studies them as well. But the paper is vast. There are many interesting results. And just to be able to say something intelligently, I just selected things for the weakest one, the Q11. And what Jim's proves is this. From the previous part, for PAQ squared, we know that all models of PAQ squared have to be kappa, like for regular kappa. And Jim shows that this is not necessarily so for PAQ11, but there are restrictions. Not every ordering is allowed, and here's this notion of strict cofinality. This is something purely set theoretic here. So kappa here is no longer regular, but model M has to have strict cofinality if M has cofinality kappa and no subset of cardinality kappa. There has no subset which is either well ordered and bounded or inversely well ordered. So there is some restriction of what can happen inside the model, which is sort of like a weaker version of regularity. And then Jim shows the following thing, that if you have this model, a weak model of PAQ11, then it is actually a model of AC0. But moreover, there is a subclass of this class of the subset of the set of second order part of the model MX, which is a model of pi11 comprehension. And from that, you have this corollary that even though this theory allows more models than PAQ squared, so the models theoretically they are not equivalent, then the PA consequences of both theories are the same. And this follows from the second part of the theorem above. And there are many other interesting things. So I say this is only a tip of an iceberg, what I quote here just to give you some flavor of what's in the paper. So he shows that the previous theorem was just characterization, but no one says that there exists models with this strict cofinality, but they do exist. So in particular, there is a model of PAQ11 of cardinality Aleph1, which is not Aleph1-like, omega-1-like. And because of that, it's not a model of PAQ squared. And there is a list of questions. So here are the questions. They're like, is there a model of cardinal kappa? Which is kappa-like for some regular kappa, but it's not a model of PAQ squared. This perhaps something looks similar to what I was asking about. We don't really know what all models of PAQ squared look like. We only know those models that Schmerl and Simpson constructed. But are there any other? What do they look like? What kind of properties they have? We don't know. So in particular, if a model of PAQ11 is kappa-like, does it have to be a model of PAQ squared? Unlike the one in the theorem above. But also, there is something that McIntyre already proved, that in a sense, the expressive power of PAQ squared is the same that PAQ cubed and for other exponents, but there is no construction. There is no construction of a model of PAQ squared that would not be a model of PAQ cube. That would be an interesting thing to sort of, and there are many variants of these questions as well, but this is like the simplest question that you can ask. And also, which I think is a funny and sort of, there might be some very interesting combinatorics behind all those questions. Are the model of PAQ11, which are not models of Q111, when you ask about the existence of 3 unbounded sets, such that every triple, which when you take one element from each, has the property given by the formula. Anyway, so this is a paper I don't know if it was widely read, because it's very beautifully written, and there are many things there about models of second order arithmetic and the connection to those generalized quantifiers, and there are technical results, and again there are things about Greifman minimal types in it, but I'm not quite sure how many people have seen it and how many people have read it, but it would be nice to have some, maybe it's time to revisit the paper and see what else can be learned from studying it. Okay, any questions? Because I moved to the second part now. Okay, so hearing none, I'm moving to part 2, which is now about stationary quantifiers. So again, a quotation from the paper on stationary logic by Barwise, Kaufman, and Mackay from 1978. And here's what they say. Shala on page 356 of Generalized Quantifiers and Compact Logic in 1975 remarks that while the traditional second-order quantifiers are too strong, there could be generalized second-order quantifiers which are weak enough for their model theory to be nice, for example, by satisfying Leventine's column, compactness, or completeness theorems. He goes on to make several suggestions as to specific generalized quantifiers to study, and one of which is the quantifier AAS, which means for almost all countable subsets S. Subsets means subset of the domain of the structure, AAS. So here is a formal definition. So you have this quantifier AAS. So at the ranges of a countable subset of a structure, and something holds for AAS many A's. So we say then if the set of countable subset of the domain of the structure that have the property phi is closed and unbounded means that every set has a superset that has the property, and closed means that you have a family of sets that have the property that their union also has the property. And in stationary logic, you include the axiom that says that there are AA many, that for almost all A X is not in A, and that this qualifies countable structures. So the structures for this language cannot be countable, and the axiom also include what is called the diagonal intersection scheme. If you are set theorist, you understand very well what this theme says. If you're not set theorist like myself, you have to stare at it. But this is this kind of property that is used in all kinds of set theoretic proofs, for example, proof of Skolem-Levenheim theorem and similar things, when you sort of argue by transfinite induction that you somehow build larger sets satisfying certain conditions. So I will not go over this in detail, but there is something here about certain class of models which are called finitely determinate, and this class was defined by Matt Kaufman. And what it says here, you see, so this quantifier does not behave like the regular quantifiers with respect to conjunction and disjunction. There is no guarantee that there are either many B's such that phi AB, or there are many B's such that not phi AB. So this is so a structure is finitely determinate if this is the case with closed and unbounded set of countable set parameters. A bar is a sequence of set parameters, and for every sequence of first order parameters, if the structure has this property, then it's called finitely determinate. It's not clear at all whether those finitely determinate structures exist, but you will see that they do. Okay, do you have any questions about what's happening here? Well, one has to get used to this notation here, but what it says here is this schema of finite determinates. It's more or less straightforward. And what plays a big role, and I will only talk about models of cardinality LF1, although all of this applies to models of larger cardinalities. What plays a role is filtrations. So if you have a model of cardinality LF1, so this sequence of subsets, M alpha less than omega 1 is a filtration if all those sets are countable, if they form an increasing chain of elementary substructures. So in particular, they are all elementary substructures of the whole model. And then for limit lambda, you closed under unions. And this property, the set property, I will refer to as continuity, because I will also consider other sequences of subsets of length omega 1 that may not be continuous in this sense. So, but filtrations, all filtrations are continuous. Okay, so again, so much about this stationary logic comes from a paper of Eklof and Meckler from 1979. And in particular, they say exactly, they did this criterion for finite determinanteness of structures. Look, and there are symbols, and you don't have to look at those symbols too much. It just says that a structure of cardinality LF1 is finitely determinate if it has a, okay, sorry about that again, please. It has a filtration such that if you take any two finite sequences in this filtration, ordered the same way. So here they ordered in an increasing way, alphas, M alphas, and M betas. And then if you take them, you add additional predicate symbols to the language to talk about the first order theory of this expansion. And then you take C bars are parameters from, you go up in the sequence until you find structures that are not the same, because, some initial segments, those M alphas and M betas could be the same. You go to the first level when they differ, but you still can take parameters from the intersection at the first place when the sequences differ. And if you include all that information, the structures must be elementary equivalent. And if this happens, then the whole structure N is finitely determinate. Okay, so that's some messy criterion, but at least something that we can understand better than the original definition of finite determinate, as it translates something from stationary logic to ordinary logic. And then there is a very beautiful, characterization of stationary logic elementary equivalence for finitely determinate structures, if M and N are finitely determinant or determinant of power LF1, that they are elementary equivalent in stationary logic, if and only if they have filtrations, such that, okay, this is so much simpler. Take any two sequences of those countable substructures in filtration, ordered in the same way with respect to inclusion, that these structures are just elementary equivalent. And if this happens, then they are much more, so then M and N are elementary equivalent in stationary logic. Okay, so this is all general. This is a general model theory. So, but this is interesting because now we have all kinds of interesting things that we know about our models of arithmetic of cardinality LF1, but in particular omega-1 like models. So we will be looking at filtrations of omega-1 like models, and every recursively desaturated model can be filtrated in such a way that those substructures you're looking at are elementary initial segments. And because of that, they're all isomorphic to one another. So they can be built, you know, as unions of elementary chains of structure of substructures. They all just identical to one another, not just elementary equivalent like in Eklov macro criterion, but simply isomorphic. Okay, so but there is more. Okay, so I will be looking at structures that I call LK filtrated, and this is something to those Zworyński who looked at theories of pairs. You take a recursively desaturated model K and its elementary extension that's also recursively saturated and also countable, and you look at the theory of the pair, and then there are many ways, there are actually many different ways of seeing that there are continue many theories of such pairs. All kinds of things can happen. This both L and K. L is isomorphic to K. K sits inside L as an elementary substructures, but the way it sits inside is it's, you know, there are continue many ways in which this can happen. But now, if I fix one of those pairs, L and K, you start with one pair like that I can construct an omega-1 like model. I start with K, and then I keep making elementary end extensions in such a way that each next pair is isomorphic to this one pair that I started with. So I continue the same pattern all the way up to omega-1, and I make it a continuous chain. So it will become those K alphas form a filtration, and then I take this model that's the union, and I call it NLK, and I say, oh, this model, so this is an omega-1 like recursively desaturated model that is LK filtrated. It's built by this repeating or iterating along omega-1 the same pattern of elementary end extensions. Okay, so they will play a role. So something about those LK filtrations. So not every omega-1 like model. Now I'm only talking about models of PA. It's not mentioned anywhere here, but we're doing model theory of PA. So look, but also you can construct those omega-1 like models in many other ways. You can change the pattern and take the isomorphism type of each next extension when you look at the pair, a model M alpha and M alpha plus 1 when you build an omega-1 like model. So there is no reason for there to be any filtration at all. Any consistent pattern, you can change the pattern. By the way, so there are lots and lots of models that are not LK filtrated for any pair LK. But now, if N is LK filtrated, then because this filtration is unique up to isomorphism. It has to be the same pattern because they have to meet on a closed and unbounded set. You do some set theory here, and then you show that if a model is filtrated, it's filtrated in only one way. Okay? And then there are specific things. I'm not quite sure how general. There might be some more general model theory here, but I know how to prove these things in case of recursively desaturated models of PA. Then that if you have a model that's LK filtrated and you have this filtration, that at the bottom of the third bullet, you know that the whole model with each of M alphas has the same first order theory as L, with K. So they all look the same, they have the same theory, but this does not necessarily mean that N with M alpha is so the next thing, if you look at those different countable models in the filtration, it doesn't mean that the pairs, the big model with one of those M alphas and the big model with some M beta are isomorphic, because they will be elementary equivalent by the fact above, but they may not be isomorphic because this isomorphism would have to be an automorphism for N, but it can happen. We can build N in such a way that N is rigid. It may have no automorphisms at all, or it may not have even elementary embeddings into itself. So the previous bullet, the third bullet, doesn't live to isomorphism. It's only about elementary equivalence. Okay, and a general question you can ask, well, so it would be nice to have some kind of classification theory, or at least sometimes that perhaps this omega-1 like model, this large, vast, uncountable structure that's built using this one chosen pattern LK. In what sense, to what extent is it determined? Could it be that the isomorphism type is already determined, or some other properties are determined by what we know about LK? And as you will see, this is not going to be the case, but now the connection to stationary logic is that by the third bullet, you can see that we can express certain facts. We can say that a model has a filtration of a certain elementary type, and then if you have NLK and L prime N prime, when LK and L prime LK prime have different theories, then these omega-1 line models will be not elementary equivalent in stationary logic, because in stationary logic you can express things about elementary theories of those pairs of the type LK. Okay, look, are you still there?
Yes.
Okay, somebody is.
Yes, we are. Yes, we are.
Yeah. So either everything's clear, or no, but do ask me questions. It's good to know that everyone that someone's there who still listens, but so I don't get carried away. But look, this is a talk about history, and there is a very short historical interlude here. Look, because I wrote a paper about N infinity omega-1 elementary equivalence of omega-1 like models of PA in '82, and so this is what I wrote in the abstract. Okay, this is what we show in the paper, that any two omega-like recurrently saturated models of PA are L infinity omega-1 elementarily equivalent, if and only if they are elementary equivalent and they have the same standard system. This was the main result of the paper. But then I wrote an introduction, and in this introduction, I will let you read it on your own.
I'm wondering about this ellipsis.
Right. So something's clearly not right. And so the paper is published in Fundamenta, and I was very happy, and then the proofs come from Fundamenta. As already, the offprints come from Fundamenta. I open it and I see this, and I see, oh, well, I use a bad word at this point. What is this? What happened? I didn't in the second. What the second one, the introduction was supposed to say was this.
Oh. That's
I checked my manuscript. I know this was not. Now these days probably I would have made a typo myself, because I would submit my manuscript, but everything was typed on a typewriter, and all the symbols were hand inserted. So I went to the office of Fundamenta, and there was this young new editor who was just hired. And she says, oh, it's terrible, I apologize. What she did, everything was already proofread and ready for, to go to the printer. But she noticed that everywhere in the paper, I talk about L infinity omega-1. There's this one place where you have L infinity omega, and she fixed it.
That's very helpful.
Anyway, so, all right. So that's here for the record. But so now, what's in this paper? What about this L infinity omega? There are no generalized quantifiers here yet, but we will get to them. But we'll get into some infinitary logic. So look, so to prove the result, I use something that I will call now ASG pairs. So this is the structures of the form LK. K and L are countable recurrently saturated. K is an elementary initial segment, but ASG stands for ascending sequences of gaps. Svorinsky would say ascending sequences of skies, but for some reason in the book we switched from skies to gaps. And so this is this pair LK is an ASG pair if there is some element in the extension that codes an ascending sequence of elements, those ANs, and such that each next element is larger than this column closure of the previous one. So every next element is above the smallest elementary submodel that contains the previous one. So those are ASG pairs. And then when I build my model NLK using this LK pattern, I will call it an ASG model. Okay, because that's a simple exercise to show that you can do that there are LK pairs, that for every countable recursively saturated K, there is an L such that LK forms an ASG pair. So they do exist. I can use them to form my to build my omega-1 like models, and those I will call ASG models. So what about them? So here is the thing about them. So what happens if I take two pairs, but this is really they are really isomorphic. K1 is isomorphic to K2, and I build two models using those pairs. Oh no, this is not what I'm saying here. And here I'm saying something different. That if I have two pairs like that, I can always find an element. What's important that you have those elements coding ascending sequences of skies, but we can make additional assumptions about those ascending sequences of skies. And then again, using Geifman techniques, using indiscernible types, you can show that you can always make those codes of ascending sequences to actually satisfy the same first order type. And if they satisfy the same third order type, and if the models have the same standard system, then there will be an isomorphism from one to the other that carries A1 to A2. And this will mean, because sequences of our length omega, the sequences will be preserved as well, then this isomorphism has to carry K1 to K2. So that means that both pairs, LK1 and LK2, actually are isomorphic. Okay, so this is literally instances, you don't get any diversity in those pairs. They're all isomorphic to one another. Okay, and so then you can use them to do certain things. So here is what you can do with them. So suppose you have two omega-1 like models, M and N, and they can be both written as a union, one of M alphas and the other of N betas, such that there is always M alpha has an extension to an M alpha plus 1, and N beta has an extension to N beta plus 1, that are those SAG pairs. The only thing that I'm not saying, this is the caveat at the end of this slide, that I am not claiming that these sequences M alpha and N alpha are filtrations. I don't make any assumptions as to what happens at the limit stage. At the limit stage, I have unions, but then I may not be able to do this because the union may not be an ASG pair. They will not. And actually quite often it will be not. So I don't have filtrations, but I can represent every omega-like model as a union of those ASG-like filtrations. And then one can prove, and it's not difficult to prove, that if you take any M alpha from the first model and any N beta from the second model, then there is a non-empty set of isomorphism from one to the other. Is such that for all alpha prime larger than alpha and beta prime larger than beta, each isomorphism from the set of H alpha beta extends to the one to then other isomorphism in H alpha prime beta prime. So there is a lot of uniformity that's happening there. These models are really built in a very similar way. They look similar, and there is kicker criterion for infinity omega 1 equivalence. It's general model theoretic theorem, but in particular from this construction or from this sort of representation of omega 1 like models, we can show that if I start with two omega 1 like models, if they have the same standard system and if they're elementary equivalent, then they actually are infinity omega 1 elementary equivalent. So it's a much stronger property. Do you have any questions? No.
I just have a question that I think you answered as you were explaining the outline, because when you put the theorem, the theorem that you proved about omega 1 like models.
Right. This is the theorem. Yes.
Right. I thought because I thought you would remember the proof well enough to have an idea whether the proof works for ZF or not. This stage obviously does, but the previous stage, which had to do with, you mentioned that you need some Geifman technology.
Right.
Would be the breakdown, because then there is
right.
no
so
such
Ali,
thing.
So in ZF, you don't really have this sort of like this nice pinpointing the smaller model by some omega sequence. You cannot really say exactly where it is, right? Is that the problem?
Yeah. You, I mean, you have the kind of analog that you have is that you could your analogous situation in ZF, don't end extend the whole model, but keep end extending the omega part of it.
Right.
So,
I see. Right. Things are complicated. But here the existence of those omega sequences that are coded simplifies things a lot.
Right.
And that's thanks to Geifman. Okay.
Very nice.
So, but we didn't get to stationary quantifiers yet. Okay, so I repeat now what I said again on the slides. So we have these NLK. If I have an SAG pair, then I get this omega 1 like NLK, the model that I called an SAG model. And then using a little bit more, and it's another paper that I noticed this later, that actually you can prove more, that all these models that are produced according as ASG pairs are finitely determinate. So that's fine. So now I can use Eckloff-Mechler criterion to see whether two given models are elementary equivalent or not in stationary logic. But also it is interesting because then in the same paper using Diamond, and actually I unnecessarily use some Kurepa trees to construct as many as possible 2 to the power continuum pairwise non-isomorphic omega 1 like models, but extending the same chosen in advanced countable model, but still non-isomorphic. You can build non-isomorphism as you construct those omega 1 like models. So at the end, you get models which are all L infinity omega 1 elementary equivalent, but very non-isomorphic. And then Jim saw how to very nice construction, and it is in our book how to do it without any extra assumptions. And so from this follows what follows here, the next theorem, right? So these models that are constructed, this sort of the great family of non-isomorphic models, well, they are L infinity omega 1 elementary equivalent by this general result that I mentioned earlier. But also now, because they are finitely determinate, they are also LAA elementary equivalent by the Eckloff-Mechler criteria. And then I mentioned this result at some conference to Shala, who was interested. He says, oh, no, you can do much more. You can actually put together L infinity omega 1 and add the stationary quantifiers. And these models that we constructed are, in fact, L infinity omega 1 AA elementary equivalent. I think this is a very nice result. It shows that these omega 1 like models are really extremely elusive in any kind of description. Now you really sort of bring big guns to try to somehow pin down the isomorphism type of a model by having stationary quantifier and being able to talk about countable elementary substructures and whatnot, and quantify over infinite countable sequences, and still you cannot really pin down them you still get this mess of many non-isomorphic models that share the same L infinity omega 1 AA theories. So I thought this nice, and this is just for the record because this is being taped. So this is the statement of this Shalach lemma that Shalach said, "Oh no, this is what holds." So what it is, these are exactly the same now filtrations M alpha and alpha, and those sets of isomorphism between one model and the other, H alpha beta, that are used for for Kikker's criterion. The only difference now is that in Kikker's criterion, they do not have to be filtrations, and in case of just arbitrary models of PA, they cannot be filtration. There are just, the model is a union of M alphas and N alphas, but there is no continuity. But if you, in addition, add continuity, then what Shalach noticed, and that you get this much stronger result. Okay, and so, but many questions are open. So there is this one construction that I gave that gives you a finitely determinate models of PA of cardinality omega 1. Are there other? Is there? Can one construct some other models that when you get maybe some interesting properties with it, and you can prove certain things about existence or non-existence of isomorphic and highly similar models? So, and so there are some candidates. And some people have looked at it. For example, can you use a pair LK such that LK is regarded saturated as a pair, as a model theoretic pair? And it's an open problem, and nobody knows. I think this is again a tempting question, and we should be able to answer it. I don't see why not, but no one has been able to do it but some people tried. And though the answer is probably no, but so we have those finitely determinate structures, and then we have this theorem that even though they are very, very elementarily equivalent, they are still non-isomorphic. But is there some other filtration that actually gives you some kind of firmer grip on the isomorphism type of this omega 1 like model that you're constructing? Maybe there's just essentially one way to do it as you go up building your model, without building in some set theoretic obstacles. And this is L infinity omega 1 with the stationary quantifier because of Shalach's lemma that talks about this particular logic. But is there any logic at all that can accomplish a task like that? So this is a very vague question, but I think probably not. And it would be interesting to see some results towards that. Okay, but there is some remark about these ASG models that's not in those old papers. That if you look at so for example, a simple argument, but it's not it's not a difficult argument, that instead of Jim's construction that gives the maximum number of non-isomorphic models, and the construction is ZFC, and it's actually very nice and clever. Here I can give you a simple example of how you can construct those SAG models so that they become non-isomorphic, because you can do all kinds of things as you go up, building, adding elementary extensions with a given isomorphism type. And because you can combine this construction with the construction of rather classless model, Kaufman models. So then you can also construct an ASG model that's rather classless. So now if there are some models, ASG model that are not rather classless, then they will be very, so they'll be L infinity omega 1 AA equivalent, but they will be non-isomorphic. And indeed it can be done. So one can prove that if you start with a countable model, countable recursively saturated model, and if you take any partial inductive satisfaction class on this model, such that the theory of the model together with the classes in the standard system. So in particular, this will happen every time when MS is recursively saturated as a pair. Then you can build an elementary end extension, and which is an ASG model, omega 1 like model. And this elementary end extension N will not be rather classless because it will actually have this satisfaction class. such that that satisfies exactly the same theory. So there are at least countably many ways of doing this, because there are countably many theories, different theories in the standard system. And so then you have an example of models just without any specific examples, and there's a simple argument that for existence of non-isomorphic, so very much similar omega-1 like models. Okay, so I'm moving now to part 3. Is there anything you would like to ask about part 2? Okay. Okay, because part 3 is the conclusion of this episode with generalized quantifiers in PA. This is another paper of Jim, but that paper is from 1995, much later. And I knew about that paper. This is in Notre Dame, but also we were at a mammals conference where I think in Easton in Pennsylvania. And so Jim titled his talk PAA in PA, because as you know, Easton is Pennsylvania. And anyway, so that was and so what is PAAA? That's a kind of unusual theory. So now there was PAQ squared, which was Peano in the logic with the Ramsey quantifier. So now this is Peano in the logic with the stationary quantifier. So PAAA is simply PA in that language. You add in the induction schema for all formulas of the stationary logic. And we also will be using this axiom DET. It says all models are finitely determinate, which means so DET is the schema that I already mentioned before, the schema of finite determinantness. Okay, which says that either there are many B's such that something holds, or many B's that something doesn't hold, and many in terms of closed and unbounded set. So Jim considered this theory PAA, and if you look at it, first of all, one big difference is that standard model is not a model of PAA, and that is because all models of PAA are uncountable. Okay, but as you will see, the good news for us is that all models of PAA have to be kappa-like, and more than that, they have to be omega-1-like. The only models of possible models of PAA are omega-1-like models, and on top of it, they are also regarded desaturated. So that's good. So we know something about those models. And so here's a proposition. This is what Jim proves quickly, that all models of PAA are omega-1-like. So how do we do that? Well, look at this formula that phi of x. It says that there is a closed and unbounded set of A that contain the initial segment up to x. Okay, so now by induction, okay, if phi of x holds, that clearly phi of x plus 1 also holds. So if you look at each initial segment of the model, with the top must be countable, but because all LAA structures must be uncountable and must be omega-1-like. Okay, so they are omega-1-like, but the question is, that seems kind of, are there any models of PAAA? So this will be answered. But this will be answered after proving. So on the way to prove this sort of analog theorem to the one that Schwell and Simpson proved for PAQ squared, that if you look at the Peano consequences of PAA plus DET schema, so this is the theory of all models of PAA together, models that are finitely determinate. And we do know that there are some. Okay, so the strength of this theory is exactly as theorems of PA that are provable with the full comprehension scheme, CA. And how this is done, I just the proofs are not as difficult as in the hyper-Ramsey theorem, but they are not easy. But some main ingredients is that Jim looks at this lambda CA, which is full second order arithmetic, so the full comprehension schema, but it's restricted to formulas. You do not allow second order parameters. You do not allow second order variables in the comprehension schema. So, but then there is a lemma about CA and lambda CA, and it comes from this earlier paper on hyper-Ramsey logic, that Peano consequences of the one and the other are the same. It doesn't make any difference, strangely. It seems like the lambda CA should be much weaker than CA, but it's not in terms of Peano consequences. And then what Jim proves is that in any finitely determinate model of PAA, the following holds. If you look at the set of all elementary initial segments such that M together with the family of sets which are coded in N, so this is this code N/M, you look at the subsets of M which are coded in N, that all of them, so there is a closed and unbounded set of those elementary submodels that are models of lambda CA. But if you are a model of lambda CA, there is plenty of comprehension. So in particular, it implies that all those models M's have to be recursively saturated. They carry satisfaction classes, because this is something that you prove in lambda CA. Lambda CA proves that there is a full satisfaction class. There is a fully inductive satisfaction class. So that's good. So if M has a closed and unbounded set of those elementary initial segments, and they're all recursively desaturated, then the whole model is recursively saturated. So now we have this picture that models of PAA plus DET, there must be omega-1 like, and they must be recursively desaturated. And then, but there is more, because using the same lemma and some general model theory completeness result that shows that Jim shows that there must be a weak model of full comprehension such that M is elementary equivalent to N, and this proves the result on my previous page. This proves this the theorem on top of this page. Okay, but so far not a single model has been built. So we don't know whether there are any models. But that's a longer story. So the bulk of the paper is actually constructing these models, but it's very similar to the construction in Schmerl-Simpson paper. You start with a countable weak model of full comprehension, and he shows that without loss of generality, you can assume that it satisfies a certain version of axiom of choice, second order axiom of choice. And then, as before in the Schmerl-Simpson paper, he converts this MX to a model of PA star by listing all defined, but now the model is countable, so we just list all sets in curly X. And then he applies a version of Geifman, those canonical extensions, by adding a sequence of elements realizing a certain indiscernible types along an ordering of type omega-1 like. And so, as I say here, much work is done. And minimal types are employed, but then Jim looks at this model and takes the reduct to PA, and it turns out that this model has the properties that are needed. So it's all very nice, but still there are some questions that remain open. I will just finishing with those questions. So we don't know whether PIA is compact, and so this is sort of, you would think that it's obviously not. Because all models of PAA have only are on cardinality at most Aleph1, because they have to have one like, but it depends on how you formulate compactness and for what languages you do that. And then again, the models that Jim constructs are finitely determinate. There are models of PAA plus DET, but are there some models which are not? Can you construct them in some other ways? Can you characterize them differently? And again, all those models of PAA plus DET were recursively desaturated, but could they be not recursively desaturated? Could they reduce to a language of PA be not recursively desaturated? So those questions are open. And again, this is a nice paper to take a look at and see what can be done, I will stop here and I will see if you have any questions. And of course, I have questions to Ali as well. Ali, have you looked at PAA or sort of AA thing for ZF?
Actually, Matt Kaufman has. So he has a paper in JSL. Yeah, from.
Oh right, I did know that, but I didn't see. I actually didn't see that. I did see the title though. Do you know what he proves there?
It gets intertwined with mildly large cardinals at the level of like n ineffable cardinals, as I remember. And I think there was a independent work by a Japanese logician by the last name of Kakuda by the same time. So
yes, I remember seeing it a lot.
Right, but going back to the first quantifier we discussed, which was
Ramsey,
the Ramsey quantifiers. I did some work on set theory with Ramsey quantifiers, but I never published it, and that was the reason I studied these Schmerl papers. This wonderful Schmerl papers. It's so things can be done, but somehow nowhere as smoothly as in the Peano arithmetic case. Actually, as you were just describing these results, a question that came to my mind, which you might remember, whether it's an open question or not, is what happens when you mix these quantifiers, the Ramsey one with the stationary? I don't even know if it's compact.
Right. But from model theoretic reason.
Yeah. I mean, I just don't remember what happens when you allow, let's say, the Magadol-Maritz quantifiers plus the stationary quantifiers.
Right, because the stationary quantifiers, it seems much longer in terms of the amount of comprehension it gives you. So definable sets, so you wouldn't get those. The Ramsey seems much weaker. Right, and if you look at the results characteristic weak models, so they for PAA, they all are model of ACA0, but then each contains a subset, which is a model of full comprehension. And this is not the case that doesn't have to be the case for Ramsey. So model theoretically, they seem to be much different, but in terms of consequences, they are the same.
Right.
No, they're not the same. One is full comprehension, then the other is pi 1-1. But if you mix them together, is it even consistent?
Exactly. Does it have?
Is there a model? Is there a model?
Yes. Right. Yes. Exactly. So Jim might.
We have to ask him. He should have been here. We'll ask him.
Okay. Good.
I'm sure he has thought about it.
Yeah. I'm pretty sure he would have thought about it and has an idea whether it's a tough problem or whether there's an easy solution.
Okay, let's thank Roman. That was a great talk.
Thank you, Roman.
Thank you.
And please continue with questions. Anyone? The floor is open. Okay, so I have a naive question. Is just the logic compact? Is the stationary logic is that?
Oh yes. So this is from this was in the Eckloff-Meckler paper that they proved.
Okay.
I think it was in the Barwise.
Oh, the Barwise. Right.
Yeah. And then Eckloff-Meckler did the finitely determinate structures. Yeah.
Right.
Yes, the only other comment I had, which has nothing, which is extremely minor, was that finite determinacy, the statement of it is very reminiscent of the ultrafilter axiom, that there are a large number of things satisfying phi or its negation. And
well, the question that I have, I thought, because it was supposed to, these were supposed to be talking about the history of the subject. And last time I mentioned this, that there is sort of, I wouldn't call it an explosion of results, but there is some kind of a sort of certain thread that goes somewhere, attractive, interesting questions and interesting answers. But this impact, and maybe Philip knows something about that, like Shelach's, motivation and other, so introduced to expand logic by adding those extra syntactic elements to the language. Well, so being model theorists, okay, so you ask this question, oh, is this compact? Is it complete? Can you do this? Can you do that? But is it useful? Okay, so from the modern point of view, you want to describe structures. You want to characterize definable sets, for a given structure. Do we know what, like in this result, when Schmer-Simpson, they say, oh, sets definable in PA Q squared are exactly the classes. I think that's very nice. So you have have some description of what you can do, and what you can't do. But in terms of some practical applications, practical quote unquote, in terms of model theoretic practice, so you have some concrete structure, and then you want to say, oh, I want to sort of get some insight. I have some non-definable objects there, but in what language can they be actually brought in? But I haven't seen much in that direction, certainly not in arithmetic. I'm not quite sure how it's working in set theory.
I know something practical, but it's
Mhm.
a completely opposite flavor. It's interesting to know when a theory allows elimination of those quantifiers. So you add them, and then you ask, when can you take them away again? So, for instance, the easiest one is the Ramsey quantifiers, when they are eliminable exactly when the theory has the finite cover property, which is a prominent property that all unstable theories. So if it does not have, I should say, yeah.
But I guess it's useful because you eliminate them, but then you say, but we are free to use them if they're convenient.
Right. But I really don't know if that. I mean, also so this was Baldwin Kieker, actually, what I just mentioned, and then Bowdish, for instance, proved that they're eliminable in all theories of modules. So it's, by the way, the finite cover property is something more. It's something stronger than just to say that uniformly definable sets that are finite have to have a bound on the finiteness. Okay, so that's kind of the thing. So the finite cover property is that, but for tuples, and it's a bit more intricate, and it's that's why it's related to these homogeneous sets. But yeah, but even those results, like has anyone ever used those quantifiers and modules to prove something? I don't know of any. It's kind of funny.
No, but that's why I spent so much time with those omega-1 like models, because it seems that not only if one is interested in them as an object of study, that you have ways of constructing them, they have those filtrations, and it seems like properties of those, that stationary logic is a very natural language to talk about how an uncountable model is built from its countable approximations.
Right.
Is there like a kappa sort of a kappa versus kappa plus sort of a generalization of this quantifier? Like there's I wouldn't know how to express it. I'm not a set theorist, but
It exists in all interpretations for any cardinal.
Ramsey's are in any cardinality.
Yeah, Ramsey is always for Aleph 0. So Ramsey is just Magiddo-Malletz for Aleph 0.
Okay.
And if you
No. This is for any regular kappa. Okay. They have Q kappa. We the parameters, the exponent and the cardinality of the set that you want. That's in the original paper. Here we didn't do that. Yeah, because
in which original paper?
Oh, that's the one that I took by quotations from the Magiddo-Malletz.
Oh, okay. Yeah.
That's the one,
That's why they're called Malletz. They're called, if for any interpretation, they're called Malletz quantifiers or Magiddo-Malletz quantifiers. But I think they really go back to Malletz.
I see, and then they were still
the Aleph 0 interpretation, they started to be called Ramsey quantifiers because it's really related to Ramsey's theorem.
Right. So
That's
here
how
was just
far I
in
remember, but it's 40 years ago. Sorry.
No, I know, but in arithmetic it certainly makes sense. I mean, in arithmetic you don't want to talk about. You talk in the model of PA. The sets are only of two kinds: finite and cardinality of the model.
Right. So I feel like perhaps the arithmetic version or the arithmetized version of this quantifier should be defined in a slightly different way, right? So to insist on these large to insist on these sets being cardinality omega.
No. Here we say unbounded. That was the
For AA.
Oh no, for NBA, but this is if you this is the sets are countable. You're looking at sequences of countable sets.
Right, and so that's what I'm saying. Maybe.
Oh, I see. So
maybe
you're going
because the restriction that these models are omega-1 like, it comes pretty much from that almost
That's right.
arbitrary sort of condition. I mean, it's not. I get it's not arbitrary, but it's in the case where we're looking at models of PA, you could theoretically ask about the same kind of thing, but for a very large model, you would want to ask about the large approximations that are
just smaller cardinality.
Yeah, so you want to say there's a closed and unbounded set of sets of size kappa if you're in a kappa plus sized model or something like that. And then I don't know, maybe the results sort of generalize immediately instead of omega-1 like, you get kappa plus like or something like that. But yeah, I don't know if you get anything out of it, but it broadens the scope of what types of models you can actually look at.
Right.
Okay. Other questions or thoughts?
Yes, I would. I was wondering, this may be naive, but if there's a connection with what Ali was talking about a few weeks ago, where you expand the language in a different way by adding, much more simply, by adding a truth definition. Can you somehow think of that as being a generalized quantifier?
How would you do it syntactically? But
yeah,
I guess maybe by thinking, having a quantifier, there exists a definable subset.
Right. There are.
Oh, I see.
It rings a bell somehow.
I haven't seen that. A quantifier that refers to definability. Although I think, as I remember, Charlie Steinhorst's thesis actually is about a quantifier. There exist indiscernibly many.
Right.
Which is the opposite in a way. But
yeah, this was in that was the time.
Yes.
On Vogue, and there's this big tome called Model Theoretic Logics, I think, or something like that. And this is the Mundici he called it. Well, it was actually a general term. What was it called? Abstract model theory, I think.
Yeah, I think abstract model theory.
I think it's a precursor in a way of these AECs that we have now, which are much more useful, it seems. But there's a lot, and then people try to define the most general. What's the most generalized quantifier? I think it's actually, doesn't it all go back to Mostovsky, who introduced the first cardinality quantifier? I think so.
Well, no, actually Ali and I. The reason I'm talking about these things, because actually Ali and I, we were at a conference, and I think it was 2007, and this was on generalized quantifiers, but we're honoring Mostovsky, and there were talks about this whole tradition. And then there was supposed to be some volume, and I gave a talk, and then there was supposed to be some proceedings volumes. They actually wrote some survey, on these things. But I don't think this paper did this ever. No, but it is true that I think Mostowski was probably the first one, and then there are some other names mentioned.
And there's
The-
another related to his quantifier in the Aleph 1 interpretation. It's also eliminability is again interesting. You can eliminate that quantifier in a theory. Let's talk about complete theory. If and only if it has no Vaughtian pairs. So it's, which is kind of rather easy nowadays, but at the time it was, everyone tried to come up with. So, but that's the easiest instance maybe of these eliminability results. And then it took off and people tried to do all kinds of stuff, and I think there is a definable. There's something also with definability of types. There's some definability quantifier, but it escapes me now. So. But these things come and go in waves, right? So I'm sure that there will be another wave when people realize, oh, this is actually very interesting if we do this and this and this.
Definitely.
And do you know? Does anyone how is it done in finite model theory when there are miniaturizations of these sort of we know that everything's finite there, but still you can compare the size of this sort of witness set to something to the size of the so negligible size as opposed to sort of like at least half of the cardinality of the model and things like that. I think those become useful, but I'm sure it has been. Actually, I know that it has been looked at, but I don't. That's this the Finnish school, finite models. Yeah. They did these things.
Yeah, they were actually involved in. I mean, also Yoko. They were in generalized quantifiers heavily in those days.
Well, linguists also love it.
Who?
Linguists.
Linguists, like Doug Westerstall and Hope, where they look at natural language and generalized quantifiers. I think Barwise even has a paper on the quantifier most.
Yeah. Philosophically, you can see that this is also interesting.
But actually, in finite model theory, I guess the quantifier that expressing more than half the elements in the model satisfy a certain property would be a natural one,
right?
Or some such thing. But and I'm sure it's been well studied. I guess Yoko would be the right person to ask.
Other questions? Okay, let's thank Roman again. A great sort of series of talks. Next week, Joel Hampkins will be speaking. We'll be back at our earlier time, so 1 p.m. New York time. And the title is escaping me, but it's on the NY Logic page, so you can take a look there. I'll stop the recording here.